Hi everyone, this is Swapnil, co-founder of Uravu Labs. We are a Bangalore-based startup and we are working towards a 100% renewable water solution.
Water, water everywhere and not a drop to drink. These lines were written in 1834, and I'm sure the author had no clue about the climate change then. But these lines perfectly describe what is going to happen to us as a result of climate change. But don't lose hope yet. There are disruptive startups working to prevent this apocalypse. In this episode of the Spotlight podcast, your host Akshay Dutt is talking with Swapnil Shrivastav, the co-founder of the green tech startup Uravu Labs. Uravu Labs literally creates water out of thin air. And in this conversation, Swapnil talks about the journey of building the technology stack to make it possible and the business opportunities they are chasing. Listen on to this insightful conversation about building a deep tech startup in India.
So I've always been very much interested in water design as well as product innovations, which are mostly focused on sustainability. So there was always one, you can say, a topic in mind that things have to become more sustainable, things have to become more efficient in the future. So there were many, you can say, people who I look up to, one of them being designers like Buckminster Fuller. Then there have been people like Nikola Tesla. So these were the people who were really inspiring, and like they was always pushing the boundaries of what to do next, what to do next. So water was one element which caught my eye, and that maybe also because I've been swimming from the age of 6. So there was one thing I really liked. Like compared to any other sport, I can swim for all day if I want to, because that's something that's very pleasurable as well as enjoyable. So there was always some love affair with water in some way or the other. So what happened that in 2013, while I was pursuing my architecture degree, there was one competition called Imagining the Future of Water and City. So that was like a global competition, and there was like some good prize money of, I think, $30,000. So we thought, me and some of my friends thought, let's just spend our summer break doing this. And we participated in that. We started exploring what all has happened in the water sector and what new technologies have come up in the past 50 years. So we realized that the last major breakthrough which happened in water sector was the reverse osmosis technology, which came out in 1960s. So for the last 50 years, there was nothing major which has happened in the water sector in terms of new technologies. So when we got this opportunity, which said explore what would be the future of water in city, we went totally futuristic and we suggested water from air would be one solution. And how I knew about water from air is again from science fiction. So Star Wars has this on their desert planet, Tatooine, they have these moisture capture units. So they were called as GX8. And so that's how they got water in their desert planet of Tatooine, because there was no other water source. So that was one of the inspirations to just come up with, okay, water from air could be a thing.
And I think Star Wars was like it inspired by Dune.
Correct. So
that desert planet.
Yeah. So even Dune, I had read Dune in 2010 before going to college, and Frank Herbert has this contractions like from your whole body moisture. And if you have seen the movie,
I did like the movie, but I'm a big fan of the book. The movie didn't do justice to the book.
Maybe they'll pick it up next later. So water from air thing was there in science fiction. And then when we started researching, then companies were already doing it. It was not something that no one has done it, or it's a totally vague concept which has only attempted. But it was only like in a very initial phases, someone has tried out in many ways. So mostly the common technology, or you can say the conventional technology to do this is use an air conditioner kind of device and keep on condensing the water vapor in the air. So what happens is whatever water vapor or humidity, moisture is in the air, it will condense, it will cool down to less than 4 or 5 degrees Celsius and will liquefy to water. So that's how the conventional process is. And when I was working on this competition, that's what we proposed. But our idea was that it could be part of a floating balloons in the sky, because at the much higher heights, you will have access to more air, and you can cover it all, the whole that floating balloon with a solar panel, and drive the energy and moisture from there and just pipe it down to your house. So that was just the initial idea. And I thought that was a bit childish, but then that's what we submitted. And then after some time, we didn't get selected for the finals, but that was idea was stuck in my. Then in 2015, I was going for my internship. So compulsory last year, 6 months is an internship and then thesis. So for internship also, I again chose a place in Bangalore where a person called, he's like a groundwater expert in India. And he was like looking at how to make our buildings or neighborhoods more sustainable through rainwater harvesting. Rainwater harvesting was one process, and second was also wastewater treatment, so that you can build self-sufficiency in a house or in a neighborhood, and you don't have to rely on groundwater or these tanker waters, which usually people bring in from longer distances. And even if you just take the case of Bangalore, we get water from Kaveri River, which is around 200 kilometers away. It's a long process which involves a lot of pumping and a lot of energy wastage. But rather than that, you can have a solution which is much more decentralized and at your house. So that was again inspiring for me, in the sense that you can do something which is more decentralized. You can do something which is very different from the infrastructure which has existed in the past 100, 150, 200 years. So then I took upon that as my thesis also, where we were looking at how to do wastewater treatment using biological plants and not rely on reverse osmosis kind of processes, which actually waste a lot of water. So for every 1 liter of water you purify, you will get 1.5 to 2 liters of wastewater. So that was again like close of my thesis. And then I was wondering whether to pursue masters or try out something with the ideas I have about water and new technologies, which would be actually. So I took the third option. And then during my last semester in college, there was one more event which further forced me to, or further inspired me to that step and continue working on these ideas I had. So that was that in Calicut, it usually rains a lot. 6 months, you'll have very heavy rains, and then 6 months of summers. But during the last semester in 2016, we had a severe kind of, let's say, a drought in our college campus in that area. So what had happened is, has laterite soil. So groundwater retention is very bad. So even if it rains a lot, almost all of it drains to the sea very immediately. So you have to rely on surface water bodies, either rivers or lakes. So the river which supplied water to our college campus had dried up from the months of January to March, I don't think. So we had to rely on these tanker water coming to our college, and there was always rationing. You will get 1 bucket per day, kind of. So that was a situation I realized, like even in a place like Calicut, which rains a lot, our infrastructure is not designed to adapt and be resilient to all these changes which are happening. And like throughout the college life, I had worked with some urban design professors, and based on the interaction and my work on that, I was also co-author in a book called E-Democracy for Smart Cities. So there also we had taken up how urban design could adapt to all these changing, either the changing climate or changing weather. So that was again a point of which kind of held me to, okay, you can go out and do something and build something new. So I started working on this water from air concept during my last semester in college. And with me was my batchmate Venkatesh, who's also co-founder at Uravu Labs. So we thought, okay, this is some new ideas which we can just take up and start working towards. So the first device we created was actually the conventional one. We just took a compressor, or instead of compressor, it's like a Peltier device, which again gives us the same, creates a very cold surface, and you can pass air over it. So that was one of the first experiments, just to tell ourselves that, okay, this works. It's not something that we just read about, but it's something which works. That was just first of our experiments, and we thought, okay, let's further give it a try. We'll do it part-time and see what happens. So then post our college, we just somehow landed in Bangalore, everyone, and thought we'll keep on working towards that. While I was also doing some freelance works with design, some startup companies. just helping them out. But on the free time, we were also building. So first we built like a 50-liter unit, and then we, in 1.5 years, we built a 200 liters per day with a conventional air conditioning technology. So in a way, we didn't.
How would this work? Just describe this 200 liter
Sure.
unit. Like, what did it look like? And
Sure. So how it works is there will be a compressor, which is usually used in conditioners or refrigerators. And there will be a refrigerant which passes to a heat exchanger. So when you run this compressor at some certain operating conditions, the heat exchanger will turn to almost 4 to 6 degrees Celsius temperature. And over this heat exchanger, you will pass ambient air. So ambient air means air all around us at normal temperatures. So when you pass this ambient air over it, there will be a certain temperature where the moisture in the air will start condensing to liquid water. So that's the basic process, and there are almost 190 plus companies all over the world which do exactly the same. There is no.
so this is like commercial grade technology right now. People are using this technology for water.
Correct. So it's basically an air conditioner, but you can describe it. I describe it as an air conditioner on steroids. You actually take more energy and then just keep on condensing that water.
Yeah. But that cold air which is coming out, that is wasteful.
Yeah.
It's not किसी का घर ठंडा हो रहा है. That's just.
So some people have tried in that way also. They'll use that air to pass into the room also, or you can again use that cool air to cool the incoming ambient air to make the system 5% more efficient. So we tried all those things also. So we actually started with a non-renewable option for all regards compared to what we are doing today.
And this would be very energy inefficient. Maybe you would consume X number of watts for every 1 liter. What was that X number? How many watts would you consume?
We had made our first unit, and Bangalore conditions where relative humidity is around 60-70%. So it consumed around 400 watt hours per liter, almost 0.4 units.
Which is not sustainable from a pricing
perspective also, as well as if you look at today also 60 to 80% of that comes from fossil fuel based power plants. So for every liter of water you produce, you would be ejecting around 100 to 500 grams of CO2. So, so it's going in the opposite direction towards what you started with. And other problem we found was whenever RH conditions say drop below 50%, this power consumption, RH, what is relative humidity? So it's actually a specific amount of water in the air divided by the specific amount of water in the air at conditions when it can condense to liquid water. So it's usually a measure of how dry or how wet environment is. So when RH relative humidity conditions drop below 50%, then we started seeing that the power consumption went as high as 800 watt hours. And when relative humidity conditions were below 40%, it went as 1 kilowatt hour. So the performance was very inefficient when RH conditions were low, as well as overall the energy source was still dependent on heat-based grid power. So that was one realization I had. As a team, we had there could be something better. There could be something more we could do, like just to push that. And then during this time also what happened, there was one event, or you can say like there was University of Alberta, Canada, and there's a non-profit called Water Illusion of Canada, and they were organizing a water innovation lab. So they had invited like an open application. So all water innovators all around the world could apply. There was like a 10-day program, and we'll go through all around India and see where all water problems are there and what people are actually doing to combat that. So there were around 20 people who got selected, and people from all over the world. And I was also one of the participants in that. So we had visited places by we saw their wastewater plant, water supply treatment plant. Then we further went to Ahmedabad, Udaipur, Ran of Kutch. So what I realized when I went to these salt plains of Ran of Kutch, you will have a lot of these workers who will be staying 2-3 kilometers apart. And there'll be just a family of 4 to 5 or maybe up to 10 people. They will work all day and then they will just have one hut like this. And outside the hut, I saw there was like a small storage tank. So that storage tank was actually for water. And what used to happen was a tanker used to come every week, fill that storage tank, and they will rely on that water for the entire week for their bathing, drinking, cooking, whatever they wanted to do. Because the groundwater is so salty, it's actually being used to make salt. So you can't really use that water for any other purpose. So then I realized like they don't even have energy infrastructure to use something like an electricity based water from regulars, let alone that they have a water source. They don't even have good energy infrastructure to run such kind of devices. So the idea was there's a lot of sun, there's a lot of like energy which falls to all these places and which is there for at least 8 to 10 hours a day. So how can we tap into that? So that's when we started thinking of, could we make this more renewable? Could we make this solar powered? Could we shift to more renewable option rather than what we are doing today? So that was one spark which kind of led to, okay, led to us thinking, let's do something more towards this. And then coincidentally in 2018, there was a competition called Water Abundance X Prize. So X Prize is a Los Angeles based foundation, and what they do is they promote like a lot of these multi-million dollar competitions where they give a very like a moonshot kind of problem statement. So the problem statement they gave was you have to make a water from air device which runs entirely on renewable energy and can make 2000 liters per day at less than 2 cents per liter. This was our opportunity to actually go out, do something and participate and see where you actually stand in the whole world where some more than 100 teams participated. So where we again had two options. We can participate with our conventional technology, which we had developed and say, okay, we can put solar panels or try to find out some other source of energy, or we can do something entirely different. That's when we started looking at desiccants. So desiccants are nothing but water vapor loving materials. So what desiccants do is when you pass air over it, they will start absorbing the moisture. So a very common desiccant which you would have seen is silica gel. So whenever you buy a thermos flask or some kind of product, you will see a small pouch. So that small pouch actually has silica gel beads. So these beads are actually very good at absorbing it. So when you leave it out in the open, they start absorbing humidity and control the moisture around it. So we thought, okay, that could be something we can start using and release that moisture back. You actually need heat. So you need heat at around 70, 80 degrees Celsius. And we thought this heat we can get from solar energy. Because solar was already used to create 80 to 100 degree hot water. It was already used for heating and drying. So that was the initial idea. And with that, we participated in X Prize. So in this Water Abundance X Prize, with this idea and all, and with the initial prototype we had made, so we got selected as a global finalist in the top 5. And we were the only team from Asia. So there around 98 or 100 teams had participated and they had selected top 5 and we were the only team from India, from Asia. And out of the 5 teams, 3 were working on a conventional air conditioning based technology. And they were either one team had paired it with biomass, one team had paired it with a windmill, one team was pairing it with some solar PV kind of.
So biomass is like the fuel source. So like instead of burning coal, you burn biomass to power it.
Yes. So they could burn biomass and then use it for their conventional source, create electricity from that. So there was one team, us team from India and the other team from Australia. They had proposed like a desiccant based technology where we use desiccants and then use solar. When we got selected in the top 5, we got a $50,000 grant. So at that time, that was really a motivation that, okay, now you have the money. Now there's some validation that this would work, this would scale. And then we realized, okay, let's start working on this properly.
In that competition, what was the capacity? Like how many liters?
Okay, so
like you told about 200 liters you had done earlier.
So isme we had just made one panel and that was some 2 to 3 liters per day.
Oh, okay. It was just like a concept. It was not an MVP.
It was more like a proof of concept that you can make something like this. But we had an idea, okay, we can put multiples of this, like in a panel, scale it. And by the way, that is something which one of our competitors does even today, but we have moved beyond that. Maybe touch that topic a bit. Then we got started because now once you get selected as a finalist, then you have to scale it up to 2000 liters per day. So from 2 liters, scaling to 2000 liters per day was again a big challenge. And then like me and Venkatesh, we both, and then some of engineers, we weren't actually experienced or even qualified to take up a project like that coming from back. So then I started expanding the team, and then I was also reaching out to many professors who have worked in either absorption systems or designers. And through that, or even solar thermal as such, energy systems. So I reached out to one professor from Indian Institute of Science, and then he connected me to Pradeep. So that's how I met Pradeep in late 28. And then we got started talking about, can we do something here? Will he be interested in this? So Pradeep is my co-founder at Uravu Labs, and he comes from a renewable energy systems and thermal systems background. So his PhD was on distributed solar thermal energy systems, heat storage, and then he was also working on waste heat recovery. And he also did his postdoc at where he was again looking at the cost and cost analysis of many thermal power plants. And he was like that. So when I got in touch with Pradeep, and then we thought, okay, now this would be something we can start working towards. And then again, the time we started looking at it and what could be something we can do about it. So that's when, and so me and Venkatesh were already there, and then Pratik joined us. And then we needed one engineer to make sure like whatever ideas we have can be translated more to a product, not just like a prototype, but more to a product. So that's when our fourth co-founder, Balaji, joined us. So Balaji was introduced from mutual friend, and then the four of us got together. And then in 2010, we incorporated Uravu Labs, and then started working full time towards making a renewable water from air system. So that was the journey till we actually got incorporated and then started building. So I would say it was not like one shot that we started working on this. Like many ups and downs and many learnings over past many years. Then ultimately we got to this stage. Yeah, so that was all a good journey where we realized it's a long process, takes time. And but the motivation was again, the world was realizing the need for new kinds of water innovations. Maybe 5-10 years back, no one really thought about water could be becoming a problem next 10-15 years. And then after 10 years, we are very late to realize that we're in a phase where such tragic things are happening already. So we thought also that it was also on our side, and there was team had like a good team has got in place, and then everyone was bringing variety of experiences, and in a way that, this problem could be taken and then solved. So that was one. And then now what we needed was like a very good technology, which we can scale, which could be made affordable over time. And that was the whole vision behind when incorporating the company and then taking it forward.
Did all four of you take up equal stakes, or like how did you navigate that?
So it was not equal stakes. Like obviously some people have more experience already. Some people had working on this for a much longer time. And then had already, this was in a way his third startup. And so he had, 4-5 years of experience, and he also brings tech expertise. So we thought, okay, when you're building something long term, you can think in that way, see what value you take.
So then how did you scale it up to make it 2-3 liters a day? Is obviously it's not a product.
Sure. So even at 2-3 liters per day, we had a technology where, what we did was we made a panel, like how you will see a solar panel. But instead of that, the panel had silica gel on top of it, and it had reflectors below it. So what will happen is during night, this silica gel would absorb the humidity, and during day, these reflectors will concentrate on silica gel. It will heat up to 80 degrees Celsius, release the vapor. This, in a way, was limiting. And this was also being tried out by one of the competitors called Zero Mass Water. And now they have changed it into Source Global. So in this design, what is happening is there are basically two units. One is your desiccant unit. Desiccant unit is absorbing the moisture, and then upon heating, you're releasing it. And there's an energy unit.
Energy unit is providing the heat.
Correct. So energy unit provides the heat during resorption. And energy unit in this panel kind of design, both the desiccant unit and energy unit are physically integrated. to each other.
Because the heat needs to come just to optimize on efficiency. You don't want the heat to be coming from a distance. Is that why?
No, that was not exactly. The intention was more like you think about a panel kind of design where you want to integrate things. Okay. You want to integrate things and you want to make,
Easy to install.
yeah, kind of thing. So want to make it very modular, and it was more inspired key. Solar panels already exist. What can you do to be a water?
Isme, how does the heating happen? Does it throw out hot air like a heater, or how does it heat that silica gel?
Sure. So we have something called like parabolic reflectors, which are like a parabolic shaped reflectors, which are made of aluminum mirrors, which have very high reflectivity of order of 95 to 97%. So these reflectors will be sitting below the silica gel tray. Okay. And whenever sunlight falls on it, they will bounce back that sunlight infrared radiation to the silica gel, and silica gel tray will get heated up.
So then why do you need the energy unit then if it's purely solar power?
So actually here the energy unit is solar heat. So what is happening is when sunlight is falling, there are two technologies which exist today. One is solar PV, photovoltaic. So that's sunlight gets converted to electricity. And other option is where sunlight, the infrared light component of the sunlight gets converted to heat. So we rely actually on heat rather than electricity. So some amount of electricity is also needed, which is like a fan, which will draw the air and pass over the silica gel. But that is like very minimal power. That's actually not driving this option. It's just needed for fans. So in this design, what was happening when everything is integrated, we are limited by two things. One is the device can only work when you have sunlight. So at the night time, there's no sun, there's no heat, which will get reflected to silica gel, and everything is integrated.
But it can continue to absorb water through the night.
Correct. So that can happen.
But that absorption will, how much could it absorb? Like a liter?
Okay. So it again depends on the amount of silica gel you put. So silica gel has a property that if you have 10 kgs of silica gel, so in about 3 hours, it will absorb 2 kgs of water. So 20% weight by weight. And so what I said, if we just listen to it again, it says 10 kgs in 3 hours. So actually silica gel just needs 3 hours to absorb moisture before it gets saturated. But then we have the whole night, which is kind of
the rest of the time is wasted.
So overall, if you see your device is, and even for desorption, what happens, it just needs 3 hours. So once say sun comes out and E4 hours out, silica gel is already desorbed and again it's becoming useless. So actually you need to run that whole system only for 6 hours. But we were using 12 hours during night, 12 hours during day, and then out of 24 hours, only 6 hours was actually getting used. Rest of the time silica gel mask.
So here, like I have a question here. The heat is on. At that time, it would not be absorbing.
Correct.
At that time, it would be sweating.
Correct. Exactly.
Okay. So you would also need an IC controller to start the heat in it once it is full. And maybe you would need some sort of a sensor to tell you that it's full, or like, how does that work? Like the intelligent controller?
Correct. Initially, we based it more on your measuring the humidity condition and the time it takes for it to get saturated. So many experiments
On device?
On device.
Okay. So you had a sensor which would sense humidity, and based on humidity, there would be an algorithm saying, okay, let it absorb for 4 hours because humidity is low. And at the end of 4 hours, then it would start the heat.
That was there, and heat would also start like as soon as sun comes out, heat will again anyway start, and it's a transparent surface where heat is just coming through the top glass.
So you can't stop the heat in any way, like if you want to.
No, so that was the problem with this design. We can't stop the heat. Like it's coming through whether you use it for 3 hours or 8 hours, how intelligently you use it. So what we did was we started, like, instead of putting a panel which is just horizontal, we tried instead of one panel, we'll put 5 panels at different angles and use the sun throughout the day, and tried all kinds of combinations and combinations. But then again, what happened was we never looked at the big picture. Initially, at least, we don't want 5 liters or 10 liters. We want 2000 liters of water. So if you make such a panel and then you have to keep on duplicating it, that's again a waste of resources. So then we came up that let's not think about integrating these together. Let's decouple them. Like heat unit could be a separate unit and desiccant unit could be a separate unit. So that's when then in 2019, we developed our first unit, which was actually a decoupled design. So here what we did was we took this silica gel and we coated it in a heat exchanger. Okay. And that heat exchanger and the desiccant unit became one unit where when you pass air over it, it will absorb the humidity. And when you want to actually desorb it and you want to apply heat, what we did was instead of having a solar collector which was focusing heat on silica gel, we instead focused this heat on a heat transfer medium, which in our case again was just hot water. So what we did was we focused this concentrated heat on tubes which were flowing with water, and this water would get heated to 80 degrees Celsius, and then this water will go into the heat exchanger which was coated with silica. So in this way, what we were able to do was we had a separate energy unit, we had a separate desiccant unit, and based on whatever timing we wanted, we had the ability to do the absorption and desorption based on wind, not based on when the sun is there. Okay. And because we were able to collect this heat in the form of hot water, that gave us the opportunity to also store that. So actually, thermal storage is in a way very cheap. What you just need is like a tank which is insulated and it can store that hot water. Okay. So what you can do is, suppose you only have sun for 8 hours in a day, but you can keep on, put some extra solar collectors, heat collectors, and let that hot water be stored in a thermal storage. So what advantage that gave us was, if you remember initially when we were speaking about time it takes for silica gel, so 3 hours of absorption and 3 hours of desorption. So one cycle is 6 hours. So because of this ability to store thermal energy in the storage tank, we were able to do multiple cycles throughout the day, even at night. So from doing one cycle, which was just 6 hours in an integrated panel, we were able to do 4 cycles in a decoupled design and do it 24/7.
How would the water heat the silica? Like through very thin pipe?
Exactly.
The way you have refrigerant, coolant, the same.
Correct.
Okay.
Correct. So we have a heat exchanger which was coated with silica gel, and then hot water will just flow through these pipes and heat up the silica gel, and it will release the moisture which was earlier absorbed, and we just condense.
And how would you heat the water?
So for heating the water, we use something called solar evacuated tube collectors. If you come in Bangalore or even parts of India, solar water heaters would be there on many rooftops. So these solar water heaters are nothing but they have a vacuum kind of tubes which are made of very thick glass, and whenever sunlight falls on it, whatever water is flowing in that will get heated. So this can,
and to what degree, what temperature can that water achieve?
So if it's a good day, an average day, we can go up to 70 to 80 degrees Celsius. It can go even as high as 100, 120 degrees Celsius if you concentrate it. But then you have to also pressurize it. For us, for silica gel kind of device, 70 to 80 degrees Celsius was pretty good.
Okay. 70 to 80 degrees Celsius water would do it in 3 hours.
So then we reached from a stage where we were just doing one cycle a day. Then we started doing 4 cycles a day with the help of this thermal storage kind of thing. So that was
your cycle at night. You could only have one cycle at night now, because once you use that hot water at night, then you can't heat it again.
No. So what we do is during the day only, we will store more than enough water for 2 cycles at night.
Okay.
So that was the advantage of having thermal storage. And
so from the thermal storage, the water goes in those thin pipes where it heats up the silica gel and the desorption happens. And then where does that water go after that?
It again goes back to the polar tubes to get heated again. But during night time, it won't go. So during night time, it will go to another storage tank, which we call as the cold tank. But then as soon as sun starts coming out in the morning, from the cold tank, it will again go to the solar tubes, get heated, go to the tank. So that was the whole loop process. So this was, if you look at all the prior art in the sense on the patent side, what all people have made throughout the years, many years, this was something very different where we have decoupled both of them. We had introduced a thermal storage unit, and we had actually jacked up the capacity utilization factor to up to 100%. So initially, if you remember, the device was running only for 6 hours a day, and now it was running 24 hours a day. So that was, huge jump in how that whole asset is being utilized instead of 6 hours versus 24. And because of such thing, we were able to actually come up with you can say a technology stack, which could be scalable, which could be made more affordable over time. And also, which was energy agnostic also in it. So as we know, this was late 2019. We had just made our first 5 liter per day unit and we were testing it till early 2020. And then, so there was a point where, again, being a hardware company and being bootstrapped, we were like, okay, do we continue with this? Or what can we do next? And there was always a time where everyone feels more low than ever because we had already achieved something and like we were going on a good track. But then there was a sudden halt and things were not in the best shape as possible. So for that, in the first wave, we started seeing it was good to keep the morale high, but then obviously you just face the consequences in some form or the other. So there was work wasn't developing much faster as we imagined. And then for 3 4 months, there was no one at office. But at that time also, we just kept running some tests just to see whether this 24-hour cycles are working or not. So that was the only thing that we. And then during late 2020, early 2021, we started, we had got one more government grant and then that also got over. So now we were from the financial point of view, there was like a big scare, like, what do we do next? How do we do this? And then COVID second wave.
Did you have fixed costs? What were your fixed costs?
So, in early days, fixed cost was mostly on human resources. We had a small team of 6-7 people. And then founders, including that. So 4 of us are founders, 3 to 4 other people. So that was the major cost. And then you had prototyping cost. But prototyping cost would be more variable. Like once you want to make it, you'll have it. But then other months were just testing. So yeah. So office rental was there. So at that time we had just taken like a very small, like a 500 square feet workshop kind of thing. It used to be a play school actually. And then we had just started working there. But it was a really nice building. It had like a building made of mud blocks. So it used to remain cool and it had a big banyan tree. So it was always really cool. So that was pleasure to work. Even if there was no work happening, but you still go. So then in early 2021, again, the COVID second wave came and again there was a pause. But then this time we started looking like reaching out to as many investors as possible. So there was and like me and Venkatesh, Balaji, we were the first time entrepreneurs. But we had a stint, but then they had not gone through that VC route. Like they were most of the time some angels and all. So we were not really connected to the VC ecosystem. And yeah, so we had gotten government grants, we had gotten some publicity, we had something in place and we knew this works. But then type VC ecosystem was not actually like looking for something like this. So initially also we had tried and some people like, this is too early for us. There's too much risk. There's no traction. This might not even work. And water industry is something which is very slow and no new innovation happen. Your customers mostly might be utilities and government. There's like a lot of this from a business standpoint, like people, they think, oh, this would work or even this technology will scale and all. But then we kept trying because we had that like kind of motivation, not just keep on trying, let's keep on trying. One day or the other, it should crack. Then, so during, you can say early 2021, we started reaching out to as many investors as possible, mainly through LinkedIn and through some of our earlier connections and cold emails. So I remember clearly we had reached out to a total of more than 300 investors. And not just in India, we tried like US, Singapore, Europe, Japan, whatever was possible, we knocked on every door. And then we had conversations with 15, 20 of them. And then some of them thought, okay, we can dive deeper. But then ultimately, then there were just like few investors who actually believed in us and then gave us our first term sheet. So that we received in around June or July 2021 last year. And then we received our first funds in September. So that was a pre-seed round and it was led by Speciale. And there were other bunch of co-investors also two from Japan and two from US. So that was our first pre-seed round. And that time there were just four co-founders, and the initial team had also left because we didn't have money to pay to them. So it was just four of us hanging by a thread and trying to see something about. But then, yeah, like after receiving the funds, knew that because what I always felt with these grants and bootstrapping and government aid was like you want to turn the wheel one full circle, but then it will turn only by 10 degrees. It will turn by 20 degrees. But unless you have that one full turn and you start, that was not happening. So unless till we got this push of that first fund investment, then only it started happening. Then it's a good trajectory, and then you can keep on innovating, keep on scaling. So that was the whole, I would say, the big push we got last year because of this first investment. And then we expanded the team. And now what we're doing is now we have that decoupled design. We have all the parameters tested. Now we are trying to look at other kind of desiccants also. So silica gel is like one of the, usually it's called like a solid desiccant. But now we are also looking at liquid desiccants, calcium chloride and these kind of oils. So these also behave a similar way, but they need slightly lower temperature, and they can also perform better in a way. They are more energy efficient, and they have also.
And what about the absorption efficiency? Like you told me in silica, it's 10 kgs can absorb 2 kgs.
Correct. So in liquid desiccant also, it's almost the same. Even with calcium chloride, we are seeing 20 to 25%, that kind of state. So uptake rate is more or less the same, but instead of 70, 80 degrees Celsius, they can work at 60, 65 degrees Celsius for the desorption. So that's an advantage, and
and same time, that will also take 3 hours.
No, this takes actually a slightly more time. Liquid desiccants for the absorption take around 6 to 8 hours, and desorption also takes 6 to 8 hours. So instead of 4 cycles, now we are doing 2 cycles.
But then why would you want to switch to liquid desiccant?
Yes.
Your number of cycles are
sure. So why we want to switch is, one is they are again further cheaper than silica gel. So silica gel is $5 per kg, and liquid desiccants are like $0.50 per kg. They're much more cheaper.
Okay, so your one-time investment comes down. The one-time installation cost.
One-time installation cost comes down. The energy efficiency is more, so the cost of the energy unit comes down. And plus also, you don't need heat exchanger. Here what happens is, so to heat up a liquid desiccant, what we do is we'll have a heat exchanger kind of thing. But then that would be more like heating up the interaction media and the liquid itself. Like instead of heating a heat exchanger, sticks on, and silica gel is put on the heat exchanger, you're just directly heating the liquid desiccant. So it's much more economical. You don't have to have a work to stick it and then heat it. So that's
then this liquid desiccant is going through pipes.
No, so liquid desiccant is not going through pipes. Liquid desiccant is like in a tank. And when we want to do absorption, what we do, pass it through media which has perforated walls kind of thing. So this liquid desiccant keeps on getting showered at these perforated walls. And when you pass air over it, these walls provide a surface area.
So there's like a jali, you have that, just a cooler with ghas ka, like there's a wall. So similar to that, it's obviously more high tech than that, but that concept is same. Like it's falling on a wall of surface where it is absorbed. Okay. Okay. And there is some fan which is pulling in air or something.
Exactly. Like so for absorption part, this is what we do. Like liquid desiccant will fall on this media, and it will interact with the air and it will absorb the moisture. So this is the absorption part. And we want to do this desorption. What we'll do is the hot water heat exchanger will heat up the liquid desiccant in the tank itself. And then again, we will pass that air over this filter media. But this time it will be in a closed condition. It won't be interacting with outside air, and it will release the moisture and it will just condense. So the engineering wise, the system has become much more simpler. And the scale also will be much more easier for us to scale. So now we have both the machines. We have silica gel machine also. We have this liquid desiccant machine also. But we think liquid desiccant would be easier to scale. And you move forward.
And in this water is pure, ready to drink?
Yeah. So air naturally doesn't have any minerals. Air is devoid of any minerals. So whatever water we get is actually pure distilled water. So to make it drinkable, what we do is we pass it through a mineral cartridge. And then mineral cartridge will balance the pH and the total dissolved salts and make it potable for.
Okay, got it. Okay, and what is the capacity of one plant? What one unit? Like how many liters a
Yeah.
day?
So now we have a 5 LPD, which is, fully tested and ready to go for pilots. And we also have a 20 liters per day in-house.
And so at 5 or 20 liters per day, this is it's not a compelling product, na? That will have a lot of buyers for it.
Correct. So that's when I would like to like how we are trying to position the whole concept and like what target sector we are going towards. So, like the whole concept of renewable water, what makes it renewable is one is you have this abundant, inexhaustible moisture in the air. And this moisture in the air is the volume wise, it's 6 times what we have in all the rivers combined. So you take all the rivers on the surface of the earth, take that volume of water, multiply by 6. That's the amount of water you have in the air at any given point. And naturally, with the earth's cycle of evaporation, condensation, this whole water vapor gets replenished every 8 to 10 days. So, in a way, you have this inexhaustible supply of air. And with our technology, what we do is we make sure that the energy which is needed for the desorption process, that is also coming from renewable energy source. So it could be, solar energy, it could be biomass. Because we are decoupled the design, we can also tap into waste heat from industries. And we can also, in a way, utilize renewable electricity also, using like a heat pump kind of device. So what we realized was like first step towards targeting any market and even then scaling further was to perfect the technology as much as possible and make it flexible. So we are still at a stage where we are making sure that our technology is the most scalable, it's flexible with all kinds of energy sources. And plus it's also more efficient than all other technology options or competitors who are there in the space. Because only when you check all these major points, where of affordability, scalability, as well as being energy agnostic, then only it can, making viability for a lot of our target markets. So initially,
Currently it is energy agnostic, because it's purely solar, so there is no need for that. But what is the one-time cost for a unit? Let's say 20 liter per day unit.
Okay, like we are not measuring currently in terms of initial cost because it's still very early to comment, but we have done calculations on a levelized cost basis. Like when you get by,
What is that
solar
mean,
panels
levelized cost?
Yes. So when you buy solar panels or when you would see these large megawatt plants of solar PV panels. So what they do is they will amortize that initial capex and they will sell the electricity. So they will say the electricity cost is 5 rupees, 6 rupees per unit.
OPEX instead of CAPEX.
So if you do calculation in that way, so for a 20 liter unit, water cost will come to around 6 rupees per liter, which is like fairly high compared to say a bottled water or reverse osmosis kind of device. But when we scale to 1,000 liters and beyond, this cost can come down to as low as 2 rupees per liter. So that's the sweet spot we are aiming for. We scale the technology to at least 2,000 liters per day. And then we can arrive at this 2 rupee per liter kind of cost. And when we say energy agnostic, it doesn't mean it's just solar is the option. What I meant is because now a desiccant unit and energy unit are separate. So this energy unit can get replaced by all other kind of sources. So solar could be one way, which could provide heat at 70 degrees Celsius. What we can also do is we can use biomass waste, burn it, and then provide heat to solar or desiccant. We can also tap into waste heat from industries. So if you go to say power plants, textile industries, process industries, they will have this waste heat from boilers, from chimneys and all. So we can tap into that. So that's what I mean when I say it's energy.
Correct. Okay. So what is the way to 20 to 2,000 liters? Is it just having 100 units placed? Is that the way, or is there a more
Sure,
like a different scale up?
Yeah, like why we let go of that panel idea was to avoid duplication, because again that's a waste of resources. Similarly, in this way, what we are doing is instead of making a 20 liter and then multiplying by 100, we are going to keep on increasing the size of a desiccant. So currently, a 20 liters per day desiccant unit is the size of a small fridge. But then when we make say 100-liter unit will be.
So for a 20 liter per day, you would need, if you're doing 2 cycles a day, so that means 10 liters. So you would need 40 liters of your desiccant.
Correct.
Basically, so it's like a 40-liter capacity, which will give you 20 liters.
Correct.
So the way to scale there is that 40-liter capacity. Instead of that, if you have 400 liters, so then that automatically is 10x. So that one single unit with 400 liters.
Correct. Exactly. 40 liters is the liquid volume for the liquid desiccant. Then you will have redundancies for airflow. So unit becomes like slightly bigger than that. But then the idea is just have a very big unit with liquid desiccant and that filter media to have the process running. So
Okay. And a 40-liter unit, you said, is the size of a refrigerator.
20 liter.
Sorry. Yeah, I would like with the 40 liters of desiccant. Okay. So that unit is the size of a fridge. Okay.
Correct.
So it will be proportional. Like if I want 20, if I want 200, then it will be the size of 10 fridges.
Not exactly, but there'll be like some efficiencies which will be gained because now we say a 20-liter unit, we'll have space for putting fans and for the space for the interaction to happen. So that we would have kept more depending on that. But when we scale, it won't be like scaling. But then more or less it'll be in that way. It might be not 10x, but might be 8x.
And how will your cost per liter come down 1/3? Where is the leverage here that will make the cost come down 1/3?
So one leverage is there because, so what happens is like when you have a 20-liter system, you have desiccant, the liquid desiccant has one cost. Then your energy unit has one cost. But then 40% cost goes in your balance of system. Balance of system comprises of fan, the casing for that, the filter media, the electronics. But when you scale to say 2000 liters per day, the balance of system is not linearly scaling. Balance of system keeps on coming down, keeps on coming down. So in that way, when we scale from say 20 liters to 2000, we get these economies of scale and we are able to make it much more compact, reduce the cost of balance of system and bring all the synergies which are possible at scale and then have the lowest cost per. So that's how we achieve that.
And probably your commercial cost in terms of customer acquisition, negotiation, contracting, installation, all of those costs are fixed. So with a bigger capacity unit, costs on a per liter basis
will be less. So what we have realized is like we looked at many markets and water is one element which is used everywhere. It's lifeline resource, used in industry, used for some agriculture. So what we realize is one is like the stage we are at, plus it's being a new technology, it's costlier. It's costlier than just putting a bore well and drawing groundwater for free. Okay. So groundwater is one big problem which we are seeing not just in India now, but even in many developed countries, it's like growing rapidly. Just to take case of the Gurugram area, the rate of extraction of groundwater versus rate of recharge is 4 times. So you're drawing out more groundwater than you recharge actually. And to the extent of 4 times, not even. And there we looked at, many applications where groundwater is being used. Agriculture is one, industries are one, drinking water is one. But then agriculture is one sector where, say because of policies and cheap groundwater availability, we can't really charge farmers more for renewable water.
Yeah.
And then again, when we look at like the drinking water sector, there again, if you already have municipal water connection, then you're already paying less than 3% and it's purified and it's already subsidized for you. But then we looked at industries, and even in industries, we then narrowed down to beverage industry. So beverage industry is one where you take any beverage, whether it be your Coca-Cola, your beer, your soft drinks, your energy drinks, more than 90 to 95% of that is actually just water. All your other ingredients, which give the flavor or the profile or taste, they're all, or the smell rather, would be like hardly 2 to 8%. And if your beer, 8% would be alcohol and rest is water. Although when you go to like spirits like whiskey and all, still 60% is water and only 40% will be alcohol. So all the beverages are entirely core ingredient is water. And beverage industry utilizes more than 1,500 billion liters of water every year, which goes into their products. So just to give you like a picture of this amount of water, this is equivalent to 20% of all the water which human beings drink on a yearly basis. So 20% of all water which human beings drink on a yearly basis is being used by the beverage company in their finished products. Okay. So we look into that industry where like water is being actually getting consumed finally. So one is where it's drinking water, another industry is beverage where is water is being used to make products, and finally it's getting consumed. So we looked at 2, 3 things. One is the quality of our water is very high because you get pure high quality distilled water which you don't need to further purify entirely used for manufacturing. Second was we had no dependence on groundwater. Now if you look at beverage industry which consumes 1,500 billion liters of water annually, more than 45% is coming from groundwater. So we started looking at, if you look at the whole history of water extraction, that we would see every 2, 3, 5 years, there'll be many protests which will be happening in countries and near plants of these big factories, of big companies, whether it be some Coca-Cola plant or Nestle plant or some other plant, their water will be extracted, groundwater will be depleted in 5 years, and there'll be some protests. And it's a common narrative which we see all across the globe. But then these industries don't have to be dependent on groundwater, and we think that renewable water could be an alternative to their current use case. So that's how we, logged onto beverage industry, because another reason also being the cost of renewable water is high, but when you fill it into a product and consumer pays for it, the price premium the consumer see is going to be very less. So suppose you take a pint of beer, which is $200 and you add renewable water to it. So now the cost of water has increased from 50 paisa to say 2 rupees or 3 rupees. But to the end consumer, it's nothing. He's just paying 2 rupees extra for a more sustainable. Similarly, we thought you take more, say a Red Bull can, it costs $10 for 330 ml. So if you just replace groundwater with renewable water, we hardly 1 rupee more. So the price premium the consumer has to pay is the least when we consider beverage industry as the application. So that's where we think that would be our first target niche, and not even like a very fast sector, but more premium sector where this extra cost would be hardly like negligible in terms of for consumers. But then for the beverage customers, they can market these drinks to be in a way that these are more sustainable. These don't use groundwater. These are made more locally and distributed locally. So that's the pitch to the beverage customers. And in turn, beverage customers show to consumers that they are a brand which is bringing out more sustainable and responsible products, and also being better for the environment at the same time.
Okay. It seems like a hard sell, man. Try to convince a beverage company that to increase their input costs and take a bet. It's a big bet for them. They'll have to change their packaging completely. And wouldn't it be better for you to take out your own beverage, your own packaged water, for example? You could have a Uravu water.
Sure.
Wouldn't that be a way to show proof of concept, and then other companies might see, okay, you are succeeding, like what Google did with Android, something like that?
That's a very interesting proposition. That there are both the angles to it. One is just to create that pull. We might have to do it. We might have to show a proof of concept. Maybe not exactly like a Uravu brand, but there could be a partner brand who might be willing. It could be a restaurant chain. It could be a hospitality chain who thinks that, okay, we can do like a partnership brand. They can have their water and powered by Uravu. Or 100% renewable water could be the tag which goes into all these bottles. So that would be the one, entry point. And then obviously for the bigger beverage companies, what we tell them is we are not looking to replace your 100% water volume requirement. We are only targeting 2 to 10% of your water requirements, which could be used for a more semi-premium products. The products which are already slightly higher in value, which even if the price increases a bit, consumer is ready to pay for the other benefits it drives. And we also see that in these products, premium products, semi-premium products have higher growth rate than your normal conventional products which are out in the market. So in that way, we are not going all in and telling beverage customer, here replace your 100% groundwater, cheap groundwater with our costly water. We're just saying try out the initial 2 to 5%, 2 to 10% and see from how it goes. So even if we take the whole of that 2 to 10% market, overall the beverage industry is a $2 trillion market from the consumer spending side. And that premium, semi-premium is more than 10% of that. So it's still a more than 200
In India, what is the size? You're saying 2 trillion in India?
2 trillion globally. And in India, it's much less. Like premium segment in water is around 1,500 crores. And if you combine, say, craft beer, craft slipper, and those kind of markets, then it goes to almost 5,000 crores. So in India itself, it's still a big market. And we think that like there'll be, and beverage is a sector where every year you will have 100 products coming. So if you look at it the way that, say, how music is made, so you will have 10 artists which will make like 10 songs in a year and 80% people will be hearing those songs. But then that 20%, there'll be like 1,000 songs in the 20% people. So there's a long tail of all these songs which get released every year, but then audience is very niche, very limited. So similar in beverages also, there's a long tail of beverages. There'll be, 100 brands, each brand launching a sub-brand, many flavors, and consumer taste and profile and their needs are changing every year. So 2 years back, you didn't have these mixed cocktail mixtures, but now there are 10 brands of cocktail mixtures. Like similarly, ready to drink cocktails, iced tea, beverages. So every year new things are coming. So we also think that these new brands or products or this limited edition launches would be our initial target market where slightly higher price would be, still be a differentiator also in it. So that's the one target.
I would still say that if you have enough money in the bank, then I think you should bet on the D2C approach on your own water brand. Because see, D2C automatically means more investor interest. If you are able to launch a water brand, show that yes, there is a consumer need for sustainable water, then your valuation from an investor perspective becomes D2C valuation, which is like a different trajectory as opposed to right now you're an input to somebody else's brand. But a lot of it depends on how much money you have in the bank right now. So obviously launching D2C brand needs some investment.
Right. Definitely. Because, and like that also, what we see is, anyway, we have to keep on developing the technology, scaling the technology. But these kind of, say, a small D2C launch or a co-branded launch would be more towards creating awareness in the market as well as generating that consumer interest, which can then translate to beverage customers realizing this option would be viable or feasible or there is attractiveness to this asset. Because renewable water itself, water from air, could be a catchy thing. That many people still today, we tell them that this is what we do. There's always a sense of doubt whether it's possible or is there something cool or you're making fun of them. So I think there's also a cultural narrative which is building up that like we have to make a shift to renewables. And like when we start with these very interesting consumer applications, there could be more pull from these corporates eventually. So that's what we think. That would be a good way. Then again, of course, there are other markets like it could be rooftop units. So if you are building like a premium villa or like a row house housing and aiming for green buildings, then you can have these units on top of your rooftops, like on your rooftops generating things. Then like there are corporates who have made a conviction that they want to go 100% carbon neutral, 100% eco-friendly till 2030, 40. So one of the pillars to enable this transformation is again water, because you can't just be all yourself 100% sustainable if water as a pillar is not addressed. So there again, we can bring this drinking water as a alternative and reduce the dependence on groundwater or bottled water. So those are again the markets, but there again, they have to pay a more premium to it. The premium will be much higher compared to beverages. So it becomes a bit limiting. And then third market where our competitor like Zero Mass Water, which have now integrated into source. So where they are focused is they make those 5 liter panels. They have that panel kind of design, and for more water, they will duplicate these units. So they are focused on the impact market, installing it in African countries or in communities which don't have access to water. But their water is, we are targeting 2 to 3 rupees per liter. Their water is 20 rupees per liter on a levelized basis. So it's very costly, but then still support from CSR funding, through support from NGOs, through support from like investors who want to donate a big chunk of their money to such projects. They're able to do many projects in that impact sector. And us being 4 times cheaper than that, we can also attempt kind of market. But that is again not a like a big target in our mind. This is more like to just do these early traction, build awareness, and get those early funds, because there the unit economics don't matter. It's more about making sure that water accessibility is there and impact is there, rather than just counting on whether water is slightly costlier or slightly cheaper, because currently they don't have a good alternative. So in that way, there could be a market for those.
So, have you done on ground testing and across different locations like a hilly area or a desert area and so on?
Okay. So we have not done exactly field trials in these areas, but we have simulated those RH conditions. So even like in Bangalore, if you see over 12 months, your RH conditions will go from 80 as high as 80% to as low as even 30% in summer days. So we have got like good data for many months and over multiple hours, full 24-hour data. So through that, we are able to make sure that we are able to generate the same amount of water. So how we do that is, suppose you have an area where RH conditions are very low. So what we do is we will put more desiccant mass into that unit. So instead of like 40 liters of desiccant, liquid desiccant giving us 20 liters of water, we might have to put 80 liters of desiccant to get the same 20 liters of water. But then liquid desiccant is so cheap, it contributes just 15 to 20% of our levelized. So suppose the levelized cost of water in Chennai is 2 rupees. And if you go to Rajasthan where you have to put 4 times more liquid desiccant, then your cost will increase by 80%, which is 2 rupees will become 3 to 3.2 rupees. So that's how we see that we are able to keep the same amount output of water in all kind of average conditions, but at the initial cost will go slightly.
So, Swapnil, we are talking a couple of months after the original conversation, which our listeners just heard. What updates do you have to share with us?
So actually, a lot has happened since the many months have passed after our conversation. We were at 5 liters per day capacity during that time, but now in the past few months we have rapidly scaled first to 20 liters per day and then to 300 liters per day. So it almost has been a 60x scaling in the last couple of months,
How
and
did you do that? Like, did you was it just scaling up the size of it, or did you also do some innovations in the design?
sure, sure. So initially, our design was in a way that we can, easily accommodate more and more volume capacity. So basic design remains the same, but then because of adding more modules as well as configuring, overall control along with that, we were able to scale much faster. Plus, we have also the advantage was we already had, a good team in place, so that rapid scaling was possible with them.
Okay,
Timely help.
okay, okay. And you're running pilots for this also now?
Correct. So we are already running pilots with our 20 liter per day unit, and very soon this 300 liters per day will be scaled to even 1,000 liters per day in about next 3 to 4 months. And the idea is to work with many beverage companies. So the pilots we are running now, one is with AB InBev, which is the world's largest brewer, and the second is with Radhiko Khaitan, which is India's largest spirit manufacturer.
Hmm, hmm. So, what is your commercial arrangement with them? Is it per liter water? Like, are you basically selling water to them?
Sure. So currently, with these large companies, what happens is they have big capex budgets. So AB InBev has a capex budget of almost $1 billion. Tadico Khaitan has another $100 million capex budget. So they are okay with paying for the equipment, at this stage. But as we scale and when we speak to some other beverage companies which are maybe don't have that capex budget,
there they are more comfortable with a pay per use basis. So there will be we are trying to get some of these contracts with some smaller beverage companies. So
Hmm.
that will be on a per liter basis.
And which will be more profitable for you in the long term, like a one-time payment model or a per liter model?
So on a long term basis, pay per use becomes a much viable model because that eliminates one is that friction also of adoption. So many companies don't want that capex on their balance sheet. So that is definitely better. Plus, as we keep on scaling our technology, the cost per liter for us also keeps on coming down. So we can have healthier margins as we scale and even improve, showcase our growth much faster.
Okay. What's your target cost per liter that you want to hit?
Sure. Currently we are at about 6 to 8 rupees per liter at 300 liters per day capacity. We are trying to hit around 4 to 5 rupees per liter in next 6 months. And then once we reach around 10,000 liters per day in about 18 months, we will be hitting a target of around 2.5 to 3 rupees per liter.
Wow, 10,000 liters a day. So will this be like a very, very massive plant? Like, will it need a lot of space to set up? What is the requirement for 10,000 liters a day?
Sure. So for a 10,000 liters per day, if you look at a fully solar powered solution, it will occupy almost 4,000 square meters. So almost zero point 0.8 acres of land. And the idea is you can set up it at a bit more further away from the city, and you can fully set a whole beverage plant at that location, and then you can supply all the beverages local. So that's one idea we have.
Okay, okay. 10,000 liters a day is typically the consumption for a small beverage plant, or this is like they will still need to augment it with groundwater? Like, will it meet their entire need, or
Sure. So for very large companies like AB InBev, their typical brewery consumes anywhere from 20,000 liters to 1 lakh liters per day. So this could be, like one model, but then many smaller beverages will be, beverage customers can easily adopt it. And what we can also do is we can then have modules of 10,000 liters per day to satisfy larger requirements. So typically, some beverage customers adopting it, they might not adopt it 100%. Maybe they will first start with 50% of their capacity, then slowly move to the uh, full
Hmm,
adoption at a
hmm,
later
hmm.
stage.
Okay, okay, okay. So basically, in the long term, this is a play for corporates with land bank. Like, say, for example, a college could also be a customer because they also have the land to set
Correct.
up a plant. Or, but within city, it would be hard to set this up because of the space it needs.
Yes, yes. So within cities, definitely will be one tough thing. But we're also looking at another model where maybe we install a unit and then get the electricity from some community farm which is maybe a further away and offset it in a way that it's still renewable, but then you don't need the solar equipment right on site where you're making the water.
Okay. So that will cut down the sizing. So what will be the size requirement then for 10,000 liter?
Oh, then it will be just two shipping containers.
Oh, wow. Okay. And
Yeah.
which can be on the rooftop also. You don't need
Which can be on
land.
rooftop, yes, yes. Which can be on any. So one shipping container typically occupies around 15 square meters. So within a 50 square meter area, you can make 10,000 liters.
This was the Spotlight presented by The Podium. To listen to more such interesting conversations, log on to thepodium.in.